And so now we go back to the exercise, and the goal here is to apply this Gaussian mixture model. And the first step here is going to be to transform the data into a logarithm. And so the data, so this is kind of simulating realistic expression data, where actually the values tend to be log normally distributed. So they're kind of they tend to spread out the larger the values are, and they tend to bunch together the smaller the values are. And so this doesn't look like a mixture of Gaussians at all if we just kind of look at this raw data here. But after taking the log, so we take log base 10 of this data here, and then put it into a histogram again, and now we have this log 10 expression level, which does indeed look like a mixture of 3 Gaussians. And so we might imagine in our sample, we happen to know there are 3 cell types. And so this means that we're going to use this knowledge to build our underlying assumption that there are 3 Gaussians making up this distribution. In the second step, what we want to do is build our mixture model. And so we have this function here, mixture model. And the idea here is that we want to do this part. So we want to be able to compute the probability for each data point. So we're feeding a single data point into this function, and we're also feeding a set of parameters into this function. And so those parameters include the weights, the pi's, the means, these mu's, and the standard deviations, the sigmas. And if we have all those values plus a data point, then we can evaluate this expression here. And so the kind of key step here is that we need to do this for each Gaussian, right? So we have this summation here. And in order to compute this likelihood for this particular data point, we have to do it for all 3 Gaussians and add them together. So we make a for loop here that's going to go through each Gaussian, and that's going to allow us to feed in all the correct parameters 3 times in our case and compute this probability, which we're summing onto an empty placeholder each time and returning this as the answer. And so this is kind of from last time when we did this with a Pascal or negative binomial example. So we're doing kind of the same thing here. We have this probability function, and it's going to take an X value or a data point plus some parameters and return a probability density value or probability value. The next step is then to compute the negative log likelihood. And so the idea here is that we have this function now to compute these probabilities, and now we need to call it. So we have the input here being parameters, so those are going to be fed in by the minimizer, and then we have this fixed arguments that's also being fed in, and that's going to contain our data. And what we want to do is return a particular negative log likelihood associated with those parameters and specific to our data. And so what we need to do is go through all the data points and compute first the density, probability density. So we're going to get that from the function we went over in the last slide, so this mixture model PDF. And once we do that, we're going to compute the log of that and add that to our growing log likelihood value. And then finally, at the end, return negative -1 times that. And so this then is our loss function. And we would then feed this into our minimizer, just like we did for the Pascal distribution. In this case, we also want to supply an initial guess. So here we've just guessed uniform weights, some random values for the mean, and some kind of arbitrary values for the standard deviation as well. And then we've also added bounds here to prevent, for example, the weights from becoming negative. We also don't want the means in this case to be negative, so there's no such thing as a negative expression value. And so this will help the optimizer stay well behaved. And so we should get this fitted result at the end. In Python, if we look at the output of this result from the minimizer, we can see the final value of the negative log likelihood function, 2,613. So hopefully this is a low value. I think it is. And we also get X here is the variable that's allowed to change in the syntax of this minimizer function. And so in that case, for us, that was our list of parameters. So these are the things that are allowed to shift. And so these are the final values. So 0.3, 0.3, 0.4, 0.3, a mean at 2.6, for example. So these were the values that it found. You can see it took 75 iterations, 813 function evaluations. And so that's how it's done in practice. And something that you may or may not have encountered is, so if we were to generate some other distributions here, some may be easy, but even if they're easy, they might not necessarily have a unique solution. So if we have these two symmetric Gaussians here, and we actually plot the parameter space here as a contour plot, so we're looking at the negative log likelihood values here. So higher is worse, of course, and we're trying to find these minima. And you can see actually that there are two of them in this case. So we could either put one Gaussian here, or we could put that same Gaussian here, and it's symmetric because they're kind of the same. And so this means there's actually not a global minimum for this problem, and it's not a convex problem either. And you can also see that we have the issue of local minima in this case here. So we trying to fit 3 Gaussians to this data set, and we can see that there are some local minima that we might get stuck in, which would not be an optimal solution relative to these deeper pockets down here. So that's the minimization step. And then the next step that we're interested in is building some kind of classifier from this. So what we can do is assemble a table here of likelihoods or probabilities. And the idea here is that now that we've gotten our parameters, so we have, say, 3 Gaussians, we know the means and the variances and everything for these different Gaussians. And what we want to do is, for each data point, compute the probability associated with each of those 3 Gaussian distributions. So we can do that one by one. We go through each Gaussian and go through each data point and spit out a value. And one of those is going to be higher than the others. So let's say, we do this for the first data point, and Gaussian 1 gives us a likelihood of 0.99, whereas the other 2 give 0.005, 0.00499. And then we might say, okay, we're going to assign this data point to Gaussian 1. So this is cell type 1, in other words, based on its expression level. So maybe we can imagine that could be like a point, right here, deep in the green. It has a really low probability likelihood associated with these other 2 sets of parameters. And we will go ahead and do this in a loop. So we go through each of the Gaussians and then go through each of the data points and compute a probability. And we're adding it to this matrix, this 3 by n matrix or table, you can imagine, of probabilities, where the rows are going to be defined by which Gaussian and the columns which data point. And then at the end, we should be able to do this. So you have the green, the blue, and the red here.